various approaches to synthetic data generation. I think we'll continue. I don't have a, I'll do. Where we're going to talk about various approaches to synthetic data generation, talk about some things we've actually done with synthetic data generation, about the pros and cons and different approaches and so forth. As Kimberly says, we're going to have a fairly long intro section and then a break, and then we'll have some Q&A at the end. And that's not advancing for some reason. Beyond the hype, we thought we'd start with, some of you will know Gartner's hype cycle, which is their way of classifying where technologies are. And I guess there's a view that the way most technologies progress over time is that they start off with some kind of innovation trigger where someone has some great idea or starts bringing something to life. And then hype gradually builds up about it, and technologies typically become the greatest thing since sliced bread, and they're going to solve all humanity's problems. And then typically there's a trough of disillusionment where it turns out that it was all a bit harder than people thought, and it was all a bit overblown, and it goes into decline. But then typically for good technologies, they enter what Gartner calls the slope of enlightenment, where they start delivering something useful, and eventually they achieve the plateau of productivity, which is where mature technologies sit. And the good news is, if you can see, at the very peak of the current Gartner hype cycle for August 2022 is synthetic data. So there's definitely some hype to get over. And one of the things we're going to try and do is tease apart different approaches to synthetic data generation, and argue that some of them are actually already on the slope of enlightenment and plateau productivity, but there is other stuff that really is correctly put at the peak of inflated expectations. So what is synthetic data? Well, the easiest way to describe what synthetic data is to start off by saying what real data is. And of course, we all know what real data is. It's actual data that describes real people or real events or real businesses or real transactions or whatever. And synthetic data is what it sounds like. It's fake data. It's made up data. It's data that is literally synthesized. And the goal, of course, is usually that you share at least some of the property. The synthetic data shares at least some of the properties of some real data, or at least some potential real data. Often, perhaps usually, the ideal is to have all of the same statistical properties as the real data, so that, for example, if you build models on the synthetic data, you might get very similar models to ones on the real data. You might think of it as the ideal synthetic data double, as we sometimes talk about, compared to a real data set, is the same as the difference between two different samples from the real data set that don't overlap. So they're kind of statistically similar, but they don't have the same data points in them. Sometimes, though, you actually want to change some properties. So you want to model scenarios that you haven't actually got in the real data, or you want to try and imagine a world where some of the historical biases didn't exist and things like that. And so then you actually need the synthetic data to have slightly different properties. So implicit in what I've said, but I thought I'd bring it out, is, why is there interest in synthetic data? Well, one of the issues is that it's often difficult to access, or impossible for people to access the real data, often because of privacy reasons. So if it's personal data, obviously there are risks associated with sharing personal data, and increasingly, I think, whereas there was lots of bad practice in the past, increasingly the rise of GDPR and just general sensibilities around personal data and the rise of identity fraud and so on means that everyone's much more careful with personal data than they used to be. But even more generally, there's there's commercially sensitive data, there's and so forth, and there's now the Information Commissioner in the UK and data protection officers generally advocate a data minimization process where you only use the data that you actually need. So if you don't need all the information, you only use part of the information. If only a subset of people need access to the real personal information, then only that subset should get it. But there's a desire for a large group of people, whether it's people learning staff or just broader people in the organization, to be able to get some of the benefits of the real data without actually having to touch it. And particularly if that goes outside the organization, that becomes even more true. So there's a constant desire, for example, for universities to get access to data to train students on, but it's often difficult for them to get the right data if it's personal data or confidential data or whatever. So as I also mentioned, there's often a desire to analyze patterns or phenomena or conditions that don't exist in the real data. And so in that case, you obviously can't do it. So one example of that is to correct historical injustices. So if you think of credit scoring, for example, there was obviously a time when and to some extent still is a situation where a lot of the lending has been to a relatively narrow subset of the population. So obviously it's been male dominated, it's been white dominated and so forth. And if you want to build credit scoring models to actually work for a broader population, you can't do that if all your historical data is just on a subset. So you often need to try and correct for that sort of thing. Well, you want to do scenario planning or what if analysis and model things like, I always get too political here, but what if we had some crazy government that came in and wanted to like abolish the higher level tax rate and remove the caps on bankers' bonuses and stuff like that? We don't have data that tells us what would happen if that kind of thing happened. Sorry if there are any bankers in the room. Not saying that's a bad idea. I'm just and the other thing, the more prosaic thing, is sometimes you want to stress test with either larger volumes of data than exist or with more diverse data than exists. So what happens if we had some really bad data coming through? What happens if we had really bad things happening that don't occur in the real data? And so you at least need to damage the real data, but often it's easier just to synthesize data with the properties that you want. So we at Smart Data Foundry tend to talk about 3 different broad approaches to synthetic data generation. This is not, it's not exactly not recognized elsewhere, but this is not a standard classification scheme. It's very much our thing, but I don't think anyone would really disagree with it. So the simplest approach and the most straightforward one is random generation or constrained random generation, which are variations on the same thing. So the basic idea here is that if you're talking about tabular data, you at the very simplest level just kind of copy the names and the names of the fields that you want and the types of the fields that you want, and you just kind of randomly generate stuff within some range for each of those things. And so it has the right structure, which allows you to your processing code typically to handle it, but it doesn't have any of the right properties. It doesn't have the right one-dimensional properties for individual fields and so forth. Or maybe you do a bit more in the constrained random. Maybe you do try and get the one-dimensional distributions right. You sample some real data. Maybe you get the right ranges for things. Maybe you get the right, maybe you get some constraints in, like the close date of an account shouldn't be before the open date of the account and stuff like that. But you don't try and get the real, the correlations between all the fields, which is normally what you think of as the goal of synthetic data generation, either within a table that you're trying to get all the correlations between all the fields right, so that if you were to build any kind of model, you'd get the right thing. And even in relational data, that maybe you're trying to get the right relationships between the data in different tables, which is even harder to do. But constrained random is very simple, and I thought actually it might be nice just to show you what I mean by that. I've done it before. Here is, here is some bank account data. We'll just look at a few records. Where we've got, an account number, an open date, and a close date. Most of the close dates are null in this case, and just some basic geodemographic information, some titles and names and locations and emails and stuff, and a credit limit and a cash card number. So just very straightforward kind of stuff. And I have here just a very simple specification file that literally just has the list of field names and types in a JSON format, and I can use that to ask the system to synthesize from that data, sdf/sd/ and type, 100 records or whatever. And if I now look at those, we see that we get the same fields and we get the right types for all the data, but obviously the values are nonsense. So because all we've said is that the title has to be a string, it's just putting random strings in because it doesn't know what to do, right? So that's the simplest kind of fuzzing style or pure random generation. But we can do more than that. We can, for example, going one stage further, we can put constraints on the fields and say things like, well, surname is a string and it's got a maximum length of 10 and a minimum length of 3. And if people in irregular, it shouldn't have any nulls in it. And for people in irregular expressions, this is saying it should be a capital letter. It should be a mixture of capital letters and lowercase letters and nothing else. So we could actually do even better by saying it should be a capital letter followed by some lowercase letters and stuff like that. And if we do that, then we end up with something slightly more convincing and interesting. Constrained SDF synth, yes, that would be even better. And again, I'll just ask it to generate 100 records. And if we look at those, now it starts to be a little bit better. We start to get, you know, things that look a bit more sensible. The postcodes now have the right structure. The phone numbers now have the right structure. The email addresses look at least a bit like email addresses and so forth. And we can gradually build up the sophistication of this. We can get the one-dimensional distributions right. But all of this is still a very simplistic approach. So I just wanted to try and make it concrete. So, and people have been doing this forever. This is nothing new. And this is very useful for testing software for correctness, testing software performance, and so forth. But it's not the thing that's at the top of the Gartner hype cycle. In fact, we'd argue this is definitely on the plateau of productivity. It's been used forever. It's powerful and well known. It's high value, but and so as I've said, the minimum that you have to provide is kind of the field names and types and a target volume. You might want to put in some simple constraints, some ranges for values and so forth. And in most sophisticated cases, you might put in simple correlations, the things that say open date shouldn't be after close date and stuff like that. So the other thing, and the thing that really Gartner's talking about when it talks about synthetic data generation is the modern idea of learning-based generation. So here, the idea is, in fact, I'll show you kind of an example of how it works. The idea is that you start off with a corpus of real data. So, you know, if it was our account table, you start off with a real account table or whatever, or a real set of transactions or a real set of whatever it is you want to model. And you feed it into some kind of artificial intelligence or machine learning system that learns the patterns in that data. And you don't ask it to predict one variable from the others. You ask it just to kind of learn all the patterns in the data so that ideally it's understood everything in the data. And it spits, so it trains for a while and it spits out some kind of a model, which I've drawn as a neural network, and it quite often is a neural network. It doesn't have to be, it could be in principle any kind of model. And so the idea is this model captures all the correlations, all the information about the kinds of patterns that you have in the data. And then you perform a kind of jiu-jitsu move. This is the kind of then a miracle happens type thing on the Blackboard cartoon, where you sort of invert the model or turn it inside out in some sense. And so my version of inversion is a literal kind of inversion. Now you start from the model, you feed it into this inverted version of the software. And so it takes the patterns captured in that model and uses them to generate synthetic data that have the same kinds of patterns as are in the data, but that don't just pass through any of the original training data to produce the output data, if that makes sense. So this is the thing that Gartner is talking about as being at the top of the hype cycle. And this is the thing that's at the top of the hype cycle. It exists. There are a number of companies doing it. There are a number of approaches to it. So if you read about synthetic data generation, you'll probably hear about things called generative adversarial models or generative adversarial networks, in fact, which are pairs of neural networks where one of the neural networks is trained to predict, to learn the patterns in the model. So often the way that works is that you use what's called an autoencoder, where you train a neural network that you give a pattern, i.e. a record that you want to learn as the input. In fact, you give all the records that you want to learn as inputs. The neural network learns the patterns in those inputs, and then the thing that you try and get it to predict is the output, but you put it through some sort of squeezing thing, so that you need a smaller, a more compact representation in what people call latent space. Don't worry if this is a bit confusing, but the idea is you basically try to have a model that compresses the information in the original data and then reproduces it so that you can feed in a partial input and it produces the output, and that's called an autoencoder. And then you kind of chop off the first layer and just apply random stuff to it and see what comes out. And what you should get out is things that look pretty much like the original data. So that's what's called a general. Well, that's a variation of autoencoder. And then the adversarial bit of a network, because you have a second network that you feed real data and synthetic data, and it tries to figure out which is which. And so the idea is at the start, it's very easy for it to tell apart the synthetic and the real data. But as the learning gets better, then it ends up having more and more difficulty distinguishing between the synthetic and the real data. And when it can't do it anymore, boom, you've got a good synthetic data generator, is the idea. So there are these kinds of things. There's fully conditional specification, which is where you basically synthesize the first column and then you use the conditional distribution between the second column and the first column to generate the second column, and then you have a joint distribution between the first two columns and the third column, and you full conditional specification to condition that third column, generate the columns in sequence. There are lots of things like that. There are things called Gaussian copulars. Fully conditional specification often uses some approach to decision trees called CART. Again, don't worry if these terms don't mean anything to you. These are just terms that you'll hear as you read about the stuff. There are k-nearest neighbor and surprisal-based approaches. And there are also a number of packages for this kind of stuff. So there are open source packages. There's Synthpop, which was developed here in Edinburgh by Gillian Rabb and Peter Novak and Chris Dibbin. I say here in Edinburgh, I can never quite work out. I think they've moved around, so it's kind of partly Edinburgh, partly Napier, partly Heriot-Watt, but certainly Edinburgh. And there's also an open source package called Synthetic Data Vault that we've explored from MIT, which has a bunch of different approaches to this. The Synthpop stuff is using this CART-based fully conditional specification. And there are commercial suppliers too. There's a British company called Hazy that specializes in this stuff. There's a US company called Diveplane that has a product called Gemini. And there are a bunch of others. Tonic AI started off doing the kind of fuzzing, this simple generating test data type approach, and is gradually moving into the more sophisticated approaches. There's mostly AI. There's actually 20 or 30 or 40 of these companies around, and it's because of all the hype around it, it's rising. And I would say that the general state of things at the moment is that for a single table, like a structured database table, these systems are starting to be reasonably good. They have more trouble with, and this is where the rows are independent, so something like an account table. When you have what's often called time series data, but really data where there's dependency between the rows. So for example, the different transactions from a single person or a single account, they have more difficulty because now they not only have to get the structure across the record right, but the structure between records right, and that's harder. And where they really struggle at the moment is when you have relational data where you've got a whole set of tables that have a relational structure with foreign keys and so forth. So you have an account table, you have a customer table, you have transactions, you have call center records and so forth, and you're trying to make the patterns in all those right. They're really not up to that at the moment. I haven't really seen anything successful in that space, but that's the promise of these things. So we have we've done quite a lot of work in this area. We've licensed Diveplane, we've used Synthpop, we've used SDV from MIT and a couple of other packages. In fact, we entered, you're probably all aware of the UNEC HLG MOS, which is the United Nations Economic Commission for Europe's high-level group from the modernization of official statistics. It's a bunch of national statistical organizations that have got together that want to, again, open up data that they collect, but that they can't give out the raw data for. And so they would like to produce doubles of that they can give people that have the same general statistical properties as the real data, but that aren't going to compromise anyone's privacy. So they set up a synthetic data challenge that we participated in last year. And Victor, who's sitting in the front row, was part of that team. I was part of that team. Paula, who I hope will join us for the Q&A, but is currently on an important mission to collect her parents from the airport, was part of that team. And we lost Ewan Gardner. He used to work for NSS Scotland, the health statistics part of NHS Scotland, and has now gone to do a PhD in Canada. But we did that. And the fantastic news was we were the champion data synthesizers of the world. I like to refer to Victor as the king of synthetic data, and Paula will be coming along as the queen of synthetic data. What they did was they provided two data sets, one of which was a set of high school and student grades from the US, so what are called SAT scores, standard attainment tests, and GPA, grade point averages for first year and final year students, and just a couple of other variables like sex and gender. And this is going to be really hard to see, but so this is this small data set. And what we've actually got here is a 6-dimensional visualization where we've broken things down into quintiles on 2 of the variables horizontally and vertically, and then used the next 2 variables for each of the subplots. And the solid points, if you can see them, the blue solid points are the girls. It's probably hard to see. The red solid points are the boys or the men, I guess. And the empty ones are the synthetic points. We will make slides of it. I think we're going to make the slides available afterwards, so you will be able to see them in more detail. And what you should be able to see is that there's good clustering, that where where the things are empty, they're kind of empty both for the synthetic data and the real data. And there's generally pretty good agreement. So this is an example of a small, simple data set that we could synthesize really quite accurately using some of the open source packages there and some of the commercial packages. Yeah, as I say, it gets harder with bigger things. So this was a small data set. They also had 1.2 million records from the American Community Survey, which was a set of records about people's income, people's commute times, people's health insurance, people's couple of other ethnicity. So they had about 40 variables, about 1.2 million records. And again, we threw those into the systems and were able to do a reasonably good job synthesizing those. So it's there, but it was a lot of work. I mean, it took 4 of us 5 days, and we still weren't happy we could necessarily release them at the end of it, but it was, it was quite encouraging. So there's a lot of interest in that. You probably noticed that we've got 2 approaches and a big gap in the middle. And the reason there's another approach, which is what we're mostly going to talk about in the second half of this session, which is the one that we've invested most time in. And this is something that's also been around forever, but isn't always thought of as part of synthetic data generation. And this is what we used to call simulation and what's sometimes now called agent-based modeling. And the idea here is that you take the system that generates the data, the data that you want to analyze, and you write code that simulates that system. So if you're trying to generate banking data, you generate a set of people, a set of companies, and a set of banks, and you have the people, the agents in the system, if you like, behave, and then you collect data from them, from the simulation that is the same shape as the data that you collect from the real system. And if you do a good job with your simulation, you end up not only with exactly the right shape of data, but with the right kinds of patterns as well, because you structurally build the right kinds of patterns in. And we've spent a lot of time on this, and we'll talk about that in a minute. So I want to give you an analogy. What happens with a lot of kinds of modeling is over time, am I in trouble if I move away from the podium?
No, as long as it's still
here. Okay. With a lot of kinds of systems, we distinguish between macroscopic models and microscopic models. Physicists particularly, and a lot of us in data science used to be physicists, so we're kind of recovering. Talk about macroscopic and microscopic models. So the idea is, one of the ways of modeling the air in this room, for example, is to take a simple thermodynamics approach where we measure the pressure and the temperature and the volume and stuff like that. And we have these high-level variables that don't know anything about the details of the air in the room, of what it's composed of. They have these macroscopic properties, and we can model what's going on in the room in thermodynamic terms, just in terms of those key high-level variables. But there's also a microscope, and that's the macroscopic approach. There's also a microscopic approach, which is where we do actually say we know what the air molecules are. We know that they're 79% nitrogen and 20% oxygen and 1% whatever, argon and then some carbon dioxide and stuff, and that they have directions and they bash into each other and all that kind of stuff. And that's what's called statistical mechanics. And these two approaches have to agree in terms of what's going on overall. And what happens is, in the early days, it's much easier to work with the macroscopic things, particularly if you only want macroscopic outcomes. But obviously, if you want to know the details of what's going on, you need to go to the microscopic approach. And so we use the equations of statistical mechanics to do that. And this is what we do with climate change as well. So we started off having very high-level models of weather and climate, and we've gradually gone to finer and finer ones. And an example I was involved with, in fact, EPCC that's in this building, the Edinburgh Parallel Computing Centre, was involved with, was road traffic. So back in the old days, when people wanted to model road traffic, they generally treated the road network as a system of pipes and thought of cars or traffic as a fluid flowing through those pipes, and then thought that congestion would be something to do with pressure or turbulence, or maybe it's the pressure is congestion and the accidents of turbulence or something. And this works to a certain extent, but those of you who are really paying attention will notice cars aren't actually that much like a fluid, and it didn't actually work that well. So a guy called Stephen Druitt had a company called SIS here in Edinburgh, and he had the idea of doing a microscopic simulation where what we do is we don't treat road traffic as roads as pipes and traffic as fluid. We treat cars as little things that move along roads and have origins and destinations and drivers, and the drivers follow simple rules, like they follow the car in front and they drive about 10 miles over the speed limit, and they, for those of you who've seen Starman, they follow the standard driving rule that green is go and red is stop and orange is accelerate extremely fast. And out that he could collect origin and destination matrices because these things are collected by the DOT and others. And after a while, twiddling the knobs, he ended up being able to produce much better models using, for like a single junction, using this microscopic approach than you could for the macroscopic approach. And that ended up, we then started, so where the Edinburgh Parallel Computing Centre came in is we took that code that could do like a single roundabout or something and scaled it up so it could do the whole of the Scottish trunk road network reasonably accurately. And then those of you who've ever driven on the road 25 miles, thank us for this. Before they introduced the variable message signs on the M25, we actually simulated what would happen if you introduced variable message signs with variable speed limits on the M25, and that was used to configure those before they start. It was all quite successful. And that's essentially what we're doing with the agent-based approach to synthetic data generation, mostly in the context of financial data. So we'll talk about that in the next session. So to finish the first bit of this first session, I want to go back to Gartner's hype cycle. So I think that they're exactly right in saying that learning-based synthetic data generation is correctly at the peak of synthetic expectations, peak of inflated expectations at the moment. It's doing something, it's got a lot of promise, it probably will do a lot of stuff, but it takes a huge amount of compute. And there are some things we'll talk about in the third session that are problems with deploying it, which are mostly to do with how do you know that you're not just copying stuff from the original data? How do you make sure that you're not leaking private information when you do it? And there are approaches to that, but they're tricky. I think the sort of constrained random and fuzzing approaches are clearly on the plateau of productivity. We've been using them forever. And I think, as we'll try and demonstrate in the next session, the agent-based approaches that, again, are much older and more established, if you think of them as simulation, are actually clearly on the slope of enlightenment. And we'll show you in the next session how we've been using them with the FCA for a sprint, amongst other things, which has been quite successful. And I think that's the end of part one of the session. How am I doing for time? Good. Fantastic. Started pretty much on time. We finished pretty much on time. That's amazing. Okay, I should have said this session. You're probably all very disappointed that David Tracy's not here. This session was advertised as being led by me and David Tracy, and unfortunately, David's dad has become very ill, and he is not able to attend today, though he may join us over Zoom for the Q&A. So I'm afraid you have rather more of me than you would otherwise have got. But I have enlisted help from Victor and Emily, who are going to break up the session a bit with more light and less noise. 3, we don't want 3, we want 2. That's the wrong one as well. That's the one. So I'm going to just run straight into the second bit, and then we'll have a break. So I want to talk about this agent-based modeling, or this simulation-based approach.
My tea. You put my extra tea in yesterday. It's no longer there. I demand my extra tea. Thank you.
We did a dry run this morning. It was there this morning. I haven't even joked about the fact that this is FinTech Scotland FinTech Festival. Though it's got the wrong T in FinTech as well. I can't believe it's Scotland. FinTech Scotland has a capital T in the FinTech, whereas the Scotland FinTech Festival from FinTech Scotland has a lowercase t. Clearly something's gone terribly wrong with this slide.
My slides aren't there.
I'll tell you what, let's. It's amazing how quickly that was picked up.
Yeah. I'm used to my name being spelled wrong.
Oh my God, it's all gone. It's all gone wrong. Downloads. Maybe. That's got 2 T's, and that's got FinTech spelled the right way, but I did just correct it. Has that got your slides? That's got your slide. This is the, don't panic, folks. It's all.
Don't look behind the curtain. Everything is well.
Right. Are we in a better state to carry on? Smart Data Foundry, the organization hosting this event, has this approach to synthesizing a population of people initially behaving economically, or exhibiting economic behaviors that we call our smart agent simulation. And so what this consists of is a population of individuals and organizations, and the people earn and spend and save and interact and work and play and have all these kinds of things. They have characteristics. The organizations include businesses and governments and shops and charities and all sorts. And what the simulation does is it generates events which are recorded in event logs. And one of the most important things to emphasize is these events are not transactions, they're events. So the event is maybe that I get paid by my job, or my event is that I go to the doctor, or the event is that I pay Victor £5 or whatever. Some of those events generate financial transactions or other kinds of transaction logs. And when they do, we record a transaction from that as well, but some of them don't. And the fact that there's a separation between those, we think, is really fundamental to this, because it means we can model things like cash transactions as well as non-cash transactions. It means that we can have things like people losing their job, and that gets recorded as an event and influences future behavior, but there's not necessarily a bank transaction. I mean, there might be a bank transaction associated with finishing your job, like your payoff or your non-payoff or whatever, but there isn't intrinsically a financial transaction associated with that, and we maintain this separation. So some events generate transactions that get recorded. And there are also these state-changing events as well. So, so that's the general idea. And the way this smart agent simulation works is it's parameterized. There are quite a lot of parameters that control simulation. So we can have different populations, different areas, different languages, different distributions, and so forth. We can turn on different kinds of logging. And sorry, I'm repeating myself, but very importantly, we record these transaction logs that are like the financial transaction logs that you get from banks, or indeed, if they're making calls, the call detail records or the text message metadata that get recorded by phone companies and so forth. And this was we're using this for all sorts of things, but the most recent thing is, was it as recent as last week? London last week. Last week, the FCA, the Financial Conduct Authority, conducted one of their regular sprints, and this one was on APP fraud, authorized push payment fraud, which Emily's going to explain to you, where they had 100 people. Still Emily's son, but they had a whole bunch of people, probably around about 100, coming in to try to tackle fraud, and we supplied synthetic data for that. So another important feature of the simulation is that billing is separate from payment. So there can be the concept of sending out a bill, and that bill can either be paid or not, and there can be a delay between the bill being issued and the payment happening. And we think that there's a lot of work in generating this kind of simulation, but we think that this can actually generate, this has a number of advantages over the learning-based approach. One of which is we can model things that haven't actually happened, and we can do scenario modeling. And the other one is it's almost completely, or in fact, if you do it the right way, is completely safe in terms of privacy risks, because you don't start from a population of real data. You just start with synthetic stuff and with reference data that are things like ONS statistics that intrinsically don't breach anyone's privacy. So, and so this is very much in development, and I don't always do a great job of distinguishing between what we've got today and what we're planning. But the idea is that the stuff in bold is stuff we've already done, and the stuff that's not in bold is to come. So we have people in the thing. For the FCA thing, we ran it with 100,000 people, and those people have jobs. Some of them are on benefits, some of them have other income sources. They have commitments, they have states, they have housing costs, mortgages or rents or whatever. In principle, they have dependents or supporters, so or can have dependents or supporters. We've sort of half started modeling that, but not completely. But they have relationships, certainly. They have cash, they have bank accounts. We haven't yet modeled savings accounts, but they will have. They have demographics, so they have, well, they have age and sex. I don't think they have race at this point, but they will have. They have identities more generally and locations. They now have communications records, and to some extent, but not very much yet, they have preferences and resources and desires and needs and so forth. And that's something that we'll be adding to over time. So already quite a rich and potentially a very rich set of things describing the individuals in the simulation that affect their behaviors. We also have organizations, and in the fullness of time, I guess we would hope to do a similarly rich simulation of organizations. At the moment, we're doing what we kind of call a half modeling of organizations. So they have staff and products and services and relationships and bank accounts and identities and comms and things. and they have sales. But particularly retailers, for example, which are one of the big sets of organizations we're modeling, we only half model them today. In time, we will fully model them. But what I mean by that is that when you go to the supermarket, it always just supplies what you want and it never has to buy it in. It's like it's got, it's the world's best supermarket. It's infinitely stocked. And the world's best shoe shop, every size is always available. So they, in fact, in the simulation just get richer and richer because all they have to do is receive money. They never actually spend money apart from money that they spend paying their staff. But that's just because we're starting somewhere, and the place we're starting is with people. Eventually, those will become fully modeled as well. And so then, as I've said, there are events. And so, a timeline here for 3 people in our simulation and 4 organizations, I guess, over time flowing to the right. So what's the first one, I guess? Bob pays a salary to Alice from the look of it. And then Alice makes a cash withdrawal and Carol does some shopping. And, oh no, I'm sorry, that's not, whatever I said, maybe it was something else. But anyway, Bob makes a purchase from wherever it is, Tesco. And, there are all these things, invoices get sent out, purchases happen, Alice changes job, there's a charge from Barclays to Bob, poor old Bob gets COVID, Bob's laid off. Oh no, Carol's laid off, it's okay, it's not all bad for Bob. I'm not going to try and do it. And then you notice that Carol pays Bob £20 in cash. And so the things in red here are things that generate digital transactions to be recorded in the banking system. The things in orange are things that we record, but they don't get recorded in the banking system because, again, we're not actually quite Big Brother modeling the cash in your pocket at the moment. But we can do that in a very safe and privacy-preserving way for our entirely synthetic people. And the black things are events that affect the simulation, but that don't generate transactions of any sort. At least don't intrinsically generate transactions of any sort. And so the way, roughly speaking, that this works, which Victor's going to show you shortly, is we have a configuration file that's written in TOML, Tom's obvious markup language, which is just a simple parameter file. We have a whole load of reference data that we use. We pass the parameters and the reference data into a simulator, run it, and then depending on what we ask for, it generates a whole load of bank transactions for each bank in our simulation, and custom lists and account lists. We actually generate PDF statements as well, not really because they're directly useful for most of the modeling, but they're really useful for understanding what the simulation is doing, because we're all used to looking at bank statements and kind of see whether they look realistic. We generate population and fact sheet. Gosh, apparently we generate a fact sheet. That might be something that should be in grey at the moment, because I don't think we generate a fact sheet at the moment. And a data dictionary. And in fact, after the work that Victor's going to describe, well, Victor and Emily are going to describe on the tech sprint, we also generate telco call detail records and text message records and fraud logs and things like this. So well, again, steal Victor's thunder, but there might be some fraud in the Glen as a result of some of the work that we've done. So I think at that point, I'm going to hand over to Emily, who was actually in London for the tech sprint, who's going to tell you more about that.
Thank you. Just pop that up on there. Hello. Yes, so as Nick said, I have travelled back by train, LNER standard class, no luxury spared, back up from London just last Friday after attending the FCA APP fraud tech sprint for 3 days in London. So yes, as we have so boringly put in text on the slide, it was just run last week. Essentially, the FCA runs a couple of these every year. Each focused on a different topic. It ranges from sustainability to global anti-money laundering to women's economic empowerment. Those are some of the past ones. This one was authorized push payment fraud, a growing area of concern where consumers can be socially engineered into sending real-time payments to fraudsters. The aim of the event was to explore approaches to early detection, also looking at intervention and how better data sharing might help. So to kind of put that into some context there, according to the annual fraud report released by UK Finance, I mean, it's a very handy document. I highly recommend you go and read it if you're at all interested in this. It has become a little bit of a Bible for me since last week. As it says there, it's a definitive overview of the payment industry fraud in 2021. But in 2021, the figure of APP fraud was £583.2 million, and that is up 39% on the previous year, which is a terrifying amount of money. However, when dealing with such big numbers and institutionalized jargonistic terms like fraud and social engineering and real-time payments, it's easy to forget the true impact. It's very easy to be part of the, oh, it'll never happen to me crowd. However, these are real everyday people being scammed out of their money. Once you take out the non-personal and the business amounts of money from the 2021 figure, the personal loss still runs to the tune of over £500 million over 200,000 cases. So that's a lot of people being scammed out of a lot of money. And that's just what's reported, not to mention that about only half of this money was actually returned to the victims in the first place. And that's just what's reported, not to mention cases where people haven't reported it because maybe they haven't realized that they've been scammed, or they're just too embarrassed to mention it. You know, especially if it's some of those smaller figures that happen a lot more frequently, you may not report it because you go, oh no, that was my bad. I should never have clicked that link in the first place. So an example of that, you've got a couple of them at the bottom here, the WhatsApp and SMS scams called hi mom messages. You get a text message saying, hi mom, I've smashed up my phone. This is my new number. You might send back going, who is this? But through social engineering, they're able to answer in a way that makes you feel like, oh, maybe it is my child. And some people don't think any further, they accept that. And then later on, the request for money comes like I need to get a new phone, or, oh, I'm stuck in Spain on holiday. You know, could you send me some cash to help out? And that's how this fraud works. I'm going to give another example now of invoice fraud. Now, because actually there are 8 types of APP fraud, ranging from purchase scams to invoice manipulation, from bank and police impersonation to romance scams. So that was the hi mum one. Invoice fraud now. Imagine, if you will, that your kitchen is looking a little bit worse for wear. You think you would quite like to get it done up. Case in point, this is your kitchen on the left. You reach out to trusty builders you can trust. You've used them before. You enjoy their services. Bob, the guy that works there, is a stand-up character, really good chap. He comes in, he does your kitchen. It's looking absolutely beautiful. You thank Bob enormously for the swish work he's done on your kitchen. He says, no problem, mate, I'll send you an invoice. You receive an invoice. Dear Mr. Opfer, please find attached the invoice for your kitchen refit. Kind regards, Bob, head builder at Trusty Builders you can trust. As you can see, we have the invoice on the right there. It's all in order. You were expecting it to be about £27,000. It was a big refit, and it has account number and sort code. No problem at all. You think, I'll get to that in a minute. I'm a bit busy right now. The next morning, you receive a new invoice. Dear Mr. Opfer, apologies for the inconvenience, but I forgot to use our new bank details on the invoice you received yesterday as we've just switched bank. The attached invoice has our new details. Please use these for your payment. Thank you for your understanding. Kind regards, Bob, head builder at Trusty Builders you can trust. You think nothing of it. It's quite reasonable that someone might forget to have updated their literature with their new banking details. I know I've done it in the past. I've gone, oh no, forgot to change bank. And everything looks to be above board. It's all got their logo on it. It's from Bob at Trusty Builders you can trust. So you think, well, fine, I will send the money across to Bob. So you do so, thinking, wonderful, I have sent the money across in a reasonable amount of time. Bob will be so happy with me. A couple of days later, you receive a phone call. It's from Bob at Trusty Builders you can trust. Oh, I had to keep that one together. Bob says, Mr. Opfer, I'm just wondering, you know, I've got a big Tesco order due on Friday. I was wondering if you were able to send that money across for that kitchen refit I did for you. And you say, but Bob, I already sent that money across to you a couple of days ago. Bob says, oh, well, I haven't received that money. You said, yes, I sent it across to the new payment details you sent me. And Bob says, what new payment details? And then the penny starts dropping, the pieces start clicking into place, and you realize that second email actually wasn't from Bob. And if you go back and look through your emails, you see the first email came from Bob at trustybuilders.co.uk. The second email came from Bob at trustybuilder.co.uk. Someone has fabricated an email address and found out the details of your kitchen refit to be able to steal that money away from you and from Bob and run off with it. Now, I have run through this as quite a tongue-in-cheek kind of example, but this is based on a true story. I found this article on the Guardian website. This is genuinely something that happened to a couple, I think they were in London, where scammers had replicated an email address and sent through an invoice that completely matched, just with different bank details. So this can and does happen. And back to the tech sprint, back to where I was last week. Here we go. That's me in the bottom right delivering my presentation. 12 teams were there, busily innovating away. Over 100 people were in attendance once you include the observers. I was there as a Scrum Master and a presenter. And one of the things that really struck me was how the teams leapt upon the synthetic data as a way to fill the gap that the real data couldn't. I should explain, the FCA gained data from 3 banks. The issue there was that A, it was highly redacted, and B, it showed only information specific to each bank, i.e. you couldn't do any linkage between banks and accounts. In real data, the level of redaction means that it's impossible to identify customers in common. Now that's quite right, that you know, if your data is being provided to an event like the FCA Tech Sprint, you, the consumer, probably wouldn't want someone to be able to identify that you have a bank account with RBS and Halifax and whoever else. So that's quite right that that was the case. However, this leads to stumbling blocks for innovation because it's hard to prove a hypothesis when the level of data doesn't support cross-functional analysis. So the Smart Data Foundry synthetic data comprised of 4 banks and a raft of telecommunications data, which did allow for cross-bank connection. It contains simulated banking, calling, and messaging behavior for a population of 100,000 individuals and thousands of companies. Not only that, but the population also included fraudsters actively committing fraud. So that means that the people analyzing the data could check how well their products were performing. And all of this data generated hundreds of millions of transactions, call detail records, text message metadata, etc. And therein lies the value. So the real power of it is that it was a linked data set. It allowed for connection and analysis that could only be dreamed of in the real pseudonymized data. The ability to link banking and telecommunications data as a way to identify fraud isn't currently done commonly in real data yet in the real world. It can be done, but only by the police, and they don't tend to get involved in APP fraud. So you wouldn't have that kind of linkage available for this kind of fraud in the real world. But in synthetic data, that's the strength. It can be done, and in fact, it is a key part of Smart Data Foundry synthetic data. So over the 12 teams, the data was accessed more than 500 times as they rampantly innovated. I should mention that the solutions were all designed with customer privacy in mind, and there were experts from the Information Commissioner's Office on hand to help out. So onto some examples. This was the only picture I got of any of the slides that mentioned synthetic data because I was so engrossed in watching the presentations, but I did get the one here. One team linked telecommunications data with banking transactions to notify the bank if a user was on an active phone call at the time of the suspicious transaction, because that can be one of the symptoms of APP fraud in effect. Or they could use SMS data to identify if a user had been receiving many text messages or very large ones at around that time as well. Another team, which is the one in the picture here, came up with a way to share real-time fraud matching flags and data fields using network analysis, which would identify scammers due to the frequency that the accounts were flagged. This would also help to determine mule accounts, where the account holder themselves, they aren't the fraudster, but their account is being used for fraudulent activity. My team looked at ways to use payment references as a way to feed into a machine learning algorithm that would identify categories of transactions to help identify people at risk of being scammed. And like I said, these are just 3 examples, but there was a huge range of applications investigated, and that was just from the one event, hey? The point is that more teams used and gained value from the synthetic data during this event than the real data because it was richer, more complete, and more appropriate to the sprint. So beyond the tech sprint, what's the impact? I kind of want to look at this from a legislative perspective because it was the FCA and the PSR, like they deal in legislating financial institutions. So synthetic data allows for the creation of end goals to help design what legislation should look like, because that's, like, as I said, what they're focused on. So although there may not be payment reason standards or linkable telecommunications data now, by knowing that that's the direction we want to go in to make things safer for the future, it allows legislative bodies to know which direction to send the legislation and the planning and all the work that goes into in advance to creating the standardization. We can't just design for what's immediately in front of us, and that's where synthetic data comes in, giving financial institutions the tools to be able to innovate without risking the data of real life people. And I will now, with that, pass over to Victor, who's going to run some demos and talk about the data itself.
So that was lovely. So hope you, by the way, that's a cat. That's not a chicken on a rock. So it was pointed out, it looks like a cat. So thanks, Emily. So as Emily has mentioned, and Nick also has mentioned, Smart Data Foundry provide synthetic data for the APP fraud sprint. I'm going to explain how we learn about APP fraud, talking with experts, and then modifying our simulation to include fraudsters and to have different type of fraud, different kind of fraud in the data. So basically, we start by learning from the Financial Conduct Authority. So I used to call it, well, I'm used to call it FCA, so not the whole name, and the PSR, or the Payment Systems Regulator. So and then modify our and about different kind of frauds. So we started talking to them. So what they call fraud typologies. So these include on these talks. These include how frequent this happens, and then what are the typical sizes of values of these transactions. So on the FCA sprint, so we talk, as I say, with the Financial Conduct Authority and the PSR, but also we talk with other experts of APP fraud. So we talk with fraud analysts from HSBC, and as well one researcher from a company called Stop Scam UK. If you read it, Stop Scam UK. Which is an organization that helps banks to identify and prevent fraud. So we talk to them and we gather all that information, and we decide, I mean, time limited, we decide what type of fraud or what kind of fraud we want to stimulate and to include in our work. So what are the typologies? Well, we start with one of the most common, which is the purchase scam. So the purchase scam, these are fraud that someone makes a purchase, often through often using a marketplace such as Amazon Marketplace or eBay, or like looking an ad on a Facebook Marketplace as well. So but either they don't receive the good, or counterfeit or simply not. The goods are not in a good condition, or they just receive whatever is not expected. So often what happens is that the person purchasing it is led to use a non-preferred payment method, such as Western Union or a direct transfer, or even cash as well. So these are relatively low value, usually averaging around £1,000, usually under £1,000, these type of purchase scams are, but they are quite frequent. So this happens a lot. So with that, we also wanted to include other type of fraud, which is the mail delivery scam. So you might notice this one because even last week I just received a message, do you have a package? and you need to pay something about it. So these mail delivery scams are a kind of an advanced payment fraud. So where someone, let's just say, text or email claiming that you have missed a delivery, and then you need to pay a delivery fee, or that customs charge, or that you need to pay a custom charge before receiving a package. Yeah. So they are also low value, but they are even lower than the purchase scam. So around £20, or like between 10 and £20. But the frequency that this happens is even higher. So you receive this, like the frequency of text messages that you might receive about this, or the news about this, is way higher. So another, and finally, the last typology or type of fraud that we include is impersonation scams. Impersonation scam, or we kind of implementing a kind of impersonation, which is called a family scam. So it's basically you receive a text for someone claiming to be either your daughter or your son or any family member, and then they request you, or they ask you to send them money to a friend's account. So, and then they have no access to their own phone. So then you need to solve for the problems of this person or the people, because they are in some pickle or some troubles, and then they need to sort that out. And then you believe that. So in fact, I have a friend, but not here in the UK, is in Argentina, that his mom was scammed by this. So they called her and then told her that his son was kidnapped. So it's not a family impersonation, but it's an impersonation. So she sent money to this. So yeah, she lost a lot of money. So not very nice story. So they are often high in value. The average of these scams is around £20,000. So, but the frequency is like very low, and the success rate of this type of fraud is also really small. So, but they are very lucrative as well. So for the fraudster, obviously. So with all this information and all these typologies, so we could try to simulate that, try to introduce that in our work. So it's worth noticing that the purchase scams, it was really simple to implement, because it's just basically the way you track it is appears only in your bank data. So just as transactions. Whereas the mail and delivery scams and impersonation scams, it is more difficult, because you have to reflect on the bank and also on the communication data. So because we provide also the phone company data, so you have to have the linkage between two different entities. So what I thought it was going to be fun, or at least fun for me, is that I will talk to you through a demo of our simulation. Yes, I will just run the simulation and see how the magic happens. So basically, we provide to FCA around 100,000 people. So I will not run a simulation for 100,000 people. That's too much, and I have a small machine here. So I will just do it for 1,000 people. So it is on which one? This one? No.
No, I think it's there actually.
Oh, it's this one. Yes. So if I, by the magic of computing, if I just type make, so basically it will just run our simulation for 100 people, and in the simulation the people will spend and will interact and will shop and will live. And if there are fraudsters, there will be defrauding people and scamming people inside. But also there is fraudsters to be. So people that attempt to be fraud, but they actually never succeed in actually committing the final fraud. So if you see here, this is, hopefully it is, these are which I prefer in a different way in a list. So these are the output of our simulation. It's basically just a different folders with data inside it. We have the call detail records, and we have the events, the population, such as, for example, for a one phone company, we have the metadata for the calling, which you can show. Yes. So the destination, the origin number, the destination number, how long was the call. And also what we have is the bank transactions and the population. For example, we have as well some demographic of the people, the date of birth, the names, the phone numbers, the citizen ID. And what is more interesting, what is easy to look at is the bank statement. So for example, if I go, which is not actually like a table to work on, it's more like a visualization way of the simulation. Let's just, hopefully I always open this one. So let me just see. This one is fine. So this is one of the bank statement for Carol Kitty Powell. So basically this is 1 month of her bank transaction. The simulation is running, I think, for a period of, I think for the configuration is either what it is 2 years. So we have 2 year simulation of these people. So we have that she is receiving a salary from Toast, and also some actually receiving some money from Gemma Teresa James. So, and also she's spending a lot of money and she's paying her council tax and she likes Argos a lot. So, so she likes buying supplier. Well, yeah, that's one way. So, and then we also have another output, which is really nice, is in the bands. We have also the fraud log, which is tell us when the fraud happened or when exactly happened, what was the transaction of it. So as you can see, so there is a nice way of doing this. So the way that we code this, it is very useful because not only we can, so as Nick mentioned, what is a configuration file plus some statistical data. So given like public data from the government or whatever available data that we have or we can find. So that means that we can actually run for a different type of economy for a different country. For example, let's just say Germany. So, and then we can do that, and I can do that. Wait a minute. No. Why is it always like this? So we can type blend params equals default DE, no, DE, and then we do make. So basically just doing that, we are running for a simulation for a different economy. So hopefully everything will be running smoothly. And the generation of a statement also runs smoothly. So if I do, this will be easier for me to go to them. So we have some kind of output, the same structure that the output that we had before. But if we look again to the statement, which is the easier way to look. And nicer one. We have a lot of transactions. So the first one is okay. So we have Demin Pavel's Mans, so which lives in Kirk, Lehengand. So also the statement is actually, but this bank is back in Scotland. Yeah, so that was, yeah. So that's a nice, that German with, that might be a froster. Money laundering happening at the moment, not necessarily. So, but as you can see, all all the merchants, all the purchases is actually happening for some German company. It's worth noticing that this is not the same simulation, just with different names, with different, so this is 100 Germans using the statistic or the public statistical available in Germany for 100 German merchants, for 100 German, not 100, for German merchants, for German shops, and doing German behavior. So they were simulating whatever behavior they have is what they, or what we think, and because we have a German in our team. So what the experience of these people have. So actually, that's our team. So that's a member, which is Eric. So yes, so these will be, this is basically how we implement and how we run our simulation, and then how powerful it could be. So there is another we work on the moment. It's not as developed as the UK or as Germany, which is the Italian version. But yeah, that is, again, that's how are they called? Smart agent simulation. Smart agent simulation, yes. So thank you so much. That's it.
We're just gonna have a short break.
Yeah.
If anyone needs to go to the bathroom, grab a coffee. So if we break now and come back at 20 past, is it one enough time, and then we'll run the last set class of the session.
Oh, is it not sharing? No, it is sharing. I just needed to unmute. Okay, well, thank you everyone. Welcome back. I'm afraid it's me again, but we'll go into some Q&A soon where we'll have more. So I wanted the last thing I wanted to do was talk about some of the limitations and some of the successes that we and others have had with synthetic data. So again, I mentioned at the end of the last thing, I think you have to think about the different forms of synthetic data generation. I think they actually sit in very different places on the hype cycle, as we talked about. One of the things that you'll often see when people talk about synthetic data is, obviously one of the questions is how do you evaluate it? How do you know whether it's any use? And there are two broad classes of metrics that people think about when doing this. One set talk about utility of the data, and the general idea is that the more similar the synthetic data that you generate is to the original data, at least in the case when you're doing a learning-based approach, the better it is, so the higher fidelity the synthesis is. And obviously it will have the real pattern. So if your goal is to do some analysis or do some modeling or whatever on the fake data in place of the real data, you want that to be as similar as possible. And the other set, and there's not one metric for that. There are lots of different metrics that you can use for that, but they all generally get lumped into this idea of utility metrics. The other axis that you think about, or the other class of metrics that you think about, are disclosure risk or privacy metrics. So I've chosen to label it privacy so that ideally you'd want that. So what you'd obviously want ideally is the maximum utility and the maximum privacy, but typically there's a trade-off between these things and you can't have them. So I guess the idea is that the real data has, at least for this kind of application, perfect utility because it's the real data. It by definition perfectly matches the real data. It has the real patterns in it. But it obviously has no privacy at all because it's the real data, and whatever's in it, if it's personal data, it's personal data, and you're revealing it by definition. At the other end, if you do constrained random generation, or indeed pure random generation, you have perfect privacy because you don't start from any real data. You're only modeling fields and types and possibly distributions. So you've got perfect privacy, but you've got very low utility typically. Again, for anything where you care about the statistics of the data. And so I guess the idea is that the learning-based approach is the best you can possibly do is produce something that's got slightly lower utility than the real data. And that as you get closer and closer to the real data, your privacy risk increases, is the general idea. And so, if you have a really good learning-based solution, maybe you can get quite close to the utility of the real data and still achieve a fair amount of privacy, but there's sort of this intrinsic trade-off between the two. Good simulation-based data is always going to struggle to generate the same level of utility because you basically have to program all the patterns, and you can use reference data and you can calibrate against aggregate statistics from the real data and correlations and things. But because you're not feeding it in the first place, it's very hard to get the same level of utility. If, again, it's the case that the real data is the ideal that you're working towards. So there's generally this kind of inevitable trade-off that you meet. But it is important to note that for different applications, this looks very different. So if, for example, what you actually want to do is robustness testing, then actually often the fake data, the randomized data is significantly better because you can put really nasty data in. You can get any volume you want. You can explore all sorts of nastiness in data that just might not occur very often in the real data. You can generate it very cheaply. You can generate it on demand and so forth. So in this case, you get perfect privacy and you actually get higher utility in the real data because the real data's only got whatever happens to be in the real data. And the case that we're most interested in is, or at least the case that we've focused on most, is where you want to model something that isn't actually available in the real data. So Emily talked about in the FCA sprint, it's not that in principle you couldn't have data, and we haven't tried to build data that couldn't exist in the real world, but in the real world, almost no one has access to the linked data that we simulated because it's really only police that have that, and except in very high value fraud cases, as Emily said, the police typically don't get involved. So in our case, if you want to say, well, what would happen if we managed to link these things in a privacy preserving way so that we could actually understand more about the interactions between different banks, between the way that money mules move money between accounts, if we could understand something about the relationship between whether people are on a call when a transaction's happening, whether it's to a new person, stuff like that, which obviously have a whole lot of privacy issues of their own. But if we want to explore those kinds of things we can't get at the data that has those behaviors in it, then the sort of agent-based simulation will have significantly higher utility while still maintaining perfect privacy or very nearly perfect privacy, because again, you're not starting by feeding real data into it. In terms of things that we've done with this already, Emily mentioned the FCA runs a series of these sprints. We've provided various synthetic bank transactions for that. Obviously, the FCA is always interested in financial data. They did an ESG sprint, and we provided synthetic energy consumption data where they had macro data, but they needed micro data. And so we simulated a whole load of data that was consistent with the macro data that they had, but that gave the right sorts of distributions for individual companies and individual buildings and stuff like that. Synthetic carbon emissions data, where again, there was a forward-looking component. So you couldn't have used the real data because the real data didn't exist, but we could explore a bunch of different scenarios for how that might change going forward, which is very much like we do with the climate, of course. We've been working with TESA on generating, not actually tabular data, but sort of hierarchical JSON data for portfolio management. So the idea that the applications there are things like investments and pensions and understanding what's going on. And again, that's more in the kind of testing space that people might be aware of the open finance movement, whereby now banks have to make your data available to you digitally through apps, so you can authorize a third-party app to access your bank account, either just to read it so it can present a dashboard to you, or even to transact for you so that it can maybe move money between accounts and things like that, and you do that on an authorized basis. That model of open banking is being extended into other industries. So one of the reasons we're called the Smart Data Foundry is the business department talks about smart data as the generalization of that, of forcing energy companies to allow you to get at your data, of allowing telecoms companies to allow you to get at your data, again, on an authorized permission basis. And the same's coming to, so there's an open finance movement where the same sort of thing's coming to pensions and to investment products. And so as the companies are gearing up to work with open finance, they need test data that they can work with and that can go across companies. So again, we've been providing examples of that. And we've actually always used them for our interview process, actually, that we like to give people useful exercises to do. And again, we can't really give them real data, so we give them synthetic data. And poor old Victor, well, actually, I say poor old Victor. Victor aced the analysis that we asked him to do on the synthetic data. And in fact, he had the extraordinary experience of there was one person he was supposed to find in it, and it turned out that person was Victor, and he thought we personalized the data for him so that the person he had to find was Victor. But in fact, do not panic. It's probably not a fire.
It's a synthetic fire.
It's a synthetic fire, that's right. I think it's working. Anyway, so those are some of the things we've done, and there are applications all over the place for this kind of stuff. So one of the interesting things that's happening is this is becoming an interesting option for companies that want to share data but can't or won't share the real data externally. But it's also becoming an interesting option for companies to share data internally. So it used to be the case that if you had access to data in a bank, for example, you'd probably have access to pretty much all data in the bank. You could just look up, a celebrity's bank spending or whatever with no particular controls. And increasingly, this data minimization principle means that even within an organization such as a bank or any responsible organization, really, they will try and only give access to the people who actually need access to a particular kind of data, and only to the data that they want. And if they can give out a synthetic double of that data instead of the real data, at least to maybe like do all the trial model building and stuff like that, then a lot of the data can happen like that. Maybe a large team of people can access that, and potentially you just then validate the model against the real data or recalibrate the model against the real data after you've already figured out what all the right variables are and broadly what the weights are and things like that. So there's a lot of interest in this from within organizations, as well as for internal uses, as well as for broader sharing uses. And so NatWest, for example, who supplies data, they own an accounting company called Free Agent. Free Agent can't get access to any NatWest data because although they're a group company, that they're not authorized to do that. But again, the hope is that we're going to be able to help them to create synthetic doubles of some of the NatWest data that they will then be able to use to prove the case for getting access to the real data. So there's lots of stuff like that. So I think this is the last slide before we go into the Q&A. Things that you might want to think about if you are considering using synthetic data. One question is, how sensitive is the real data? Obviously, the more sensitive it is, the bigger the case for using synthetic data. And the more sensitive it is, the more difficult. So, sorry, I maybe haven't spelled out quite clearly enough. It's probably obvious, but the danger, the sort of intrinsic danger of the learning-based approaches is that you start off with the real data. And so the thing that you obviously have to fear is that if the model isn't very good, it doesn't spit out plausible synthetic data, it actually passes significant parts of real people or real people's personal data through. Now, there are a number of approaches to measuring that, these disclosure risk measures, but none of them are perfect. There are also some approaches, including cryptographic approaches, to avoiding that. So one of the very popular things is there's an approach called, my mind is blanking. No, why is my mind blanking? The noise that you can add to synthetic data.
Oh, okay. Laplace.
No. Well, yes, Laplace. Why is my mind blanking? I suppose the name doesn't actually matter, but there's an approach whereby you can quantify how much noise you can add to data, while no, there's so there's an epsilon that you can set, where basically as you increase epsilon, you add more noise to the data, and increase the privacy, but you gradually destroy the correlation between the original data and the real data. And so one of the approaches to synthetic data is to add noise to the data before you model it, so that in principle, the data that you are feeding into the model doesn't actually contain, with very high statistical probability, personal data that will reveal anything, and therefore you know that what's going to come up. Differential privacy. I can't believe. Thank you. Yes, differential privacy. Sometimes two parameters, epsilon and delta. Sometimes just one. But this is a way that you can, in principle, prove that it must work. Now, the difficulty with that is, as with cryptographic schemes, you have to be sure that you've implemented differential privacy perfectly in order for that to work. And what that means in practice is that you still have to check the data that you've generated if the system was exposed to real data, even if you've applied differential privacy. The second problem is that although in principle you've got this parameter, this knob that you can turn that controls how much of the real signal you leave in the data, if you set that so that it's very privacy protecting, you end up wiping out so much of the pattern that you don't end up producing very high utility data. So that there are always these trade-offs, but this approach is available. So yes, how sensitive is the data? Will it be shared externally? Again, if you're going to share it externally, you obviously have to be much more careful about disclosing stuff than if you're not going to share it externally. Is real data available in the form that you need it? If it's not available, then you probably have to go to some kind of synthetic data approach, and it's probably not going to be a learning-based approach. Kind of the same point, do the patterns that you wish to model exist? What's your use case? What aspects need to be real and what aspects don't? And again, if the data is sensitive, whether that's commercially sensitive or PII type data, then avoiding using that personal data is best practice. And how much of it do you need? Because if you've only got a limited volume available, you may need a synthetic data approach just to get to the volumes that you need. So I think that's it. Now, we hoped we were going to have 6 people on the panel, but in fact, Paula, I think, has not yet arrived. I don't know whether David's on the call. Paula has arrived. The queen of synthetic data is here.
Do we have any questions in the room?
Yes.
There we go. If we go you, and then can you come up a little bit closer? Sorry, the mics in the room are not set. Just here, just stand where I am.
I was wondering if you had any interest in synthetic health data. I thought that would be an area, and I wonder if that had been discussed and what you might do with it. I had my own ideas.
The short answer is no, we don't have any help.
That was going to be the opposite of my answer.
How is it?
So I mean, I think that obviously financial data is intrinsically private, and so there's a lot of interest in it. But health data is even more private, and so there's a huge amount of interest in synthetic data in the health sector. And I would say those are really the two sectors that are driving it. It's not a central focus for the Smart Data Foundry, but it is the case that Smart Data Foundry is supposed to be, is interest. Its whole idea is data for good and trying to take data sets and make them available for social and societal benefit. And there are very clearly links in both directions between health outcomes and financial outcomes. So poverty obviously affects health, and health obviously affects wealth. So there's a huge amount of interest in that, but health data is for most people more personal than financial data, and so it's the idea of bringing the two together is really toxic in privacy terms. But there are ideas about using synthetic data to do exactly that. Probably not initially using the learning-based approach, though people are exploring that. So there are agent-based simulations that exist for health conditions. There are also lots of people studying generating synthetic health data by starting from the real data, possibly applying differential privacy, generating models from that, but that obviously doesn't link to the financial outcomes. And it's the bringing the two together we'd be interested in. But within the university, for example, there's a project called the Data Lock, which Kathy Harrison's the lead researcher for, that's specifically looking at synthetic data for healthcare. RDS Scotland is also in this book, and that's Research Data Scotland. Their funding work in this area are interesting as well. And NSS Scotland, as I say, the fourth member of the UNECE, HLG, MOS champion world data synthesizing team, actually worked initially at NSS on synthetic data. So yeah, there's a lot of interest.
But you see, our research data Scotland, and we're definitely investigating synthesizing health data.
Absolutely. Do you want to say who you are?
Oh, sorry, I'm Linda Deere. I'm the distribution manager.
We met, didn't we?
We have, yeah.
I'm glad I mentioned RDS then.
Hi, so I work for a fintech who are doing modelling and insights into investment management. One of the challenges we face, and the question I have is around the sort of learning-based approach particularly, is around explainability. How do you feel that that factors into what you're doing and where you can use the models?
That would be so how can we explain?
Yeah, so there's the general area of explainable AI, where some of the traditional methods of doing statistics are thought to be quite easy. So there's a general concern that if you use machine learning or indeed statistical decisioning generally, you need increasingly to be able to explain how your models work. There's an area sometimes called XAI about explaining your models. And so if you have relatively simple models like decision trees, which basically start with the data and divide it up with a set of questions, typically yes, no questions, then those are quite easy to explain, at least how the models work. Traditional scorecards that are used for credit scoring are quite explainable as well, or at least superficially explainable in the sense that you get a number of points for, typically, more income and more credit cards and longer financial history and more stability and things like that, generally give you more points in credit scoring and so forth. And so those models are relatively explainable. And one of the criticisms of neural networks in particular, deep learning systems as they're called these days, but many of the fancier systems or models where modeling approaches where you take 1,000 models and combine their predictions, is it becomes very hard to explain how any decision's been made. And so that's a problem. I know you're asking specifically in the context of synthesis, but even just in the context of decisioning, it's hard to show that you're not having biased decision making if you can't explain what the model's doing. And similarly, if you're generating synthetic data, an obvious question is, well, I need to understand how it works, otherwise how can I possibly trust the stuff? And I think broadly the same thing, I think broadly the same things apply. So the two main ways that people look to do explainable AI are firstly by using some of the more scrutable, if you like, modeling methods. So things like decision trees and scorecards and systems like that. But is one comment. A second thing is, even if you build a deep learning system, maybe you try and build a second system, even if it's less accurate that does use some of the more explainable methods. And if you can show that 95% of the predictions are the same, then even though it doesn't fully explain the model, it gives you a kind of 95% explanation of the model. And the third thing is you take the models and you look at the predictions that it makes, and you explore them using data visualizations and so forth, and just start looking at patterns. So an interesting, so this might be a longer-winded answer than you wanted, but if you take scorecards, so, a scorecard might be as simple as it might have 4 components, which, say, for the sake of argument, if your income is, under £20,000, you get minus 20 points. If it's say 20,000, if it's between 20,000 and 30,000 pounds, you get 0 points. If it's about, if it's between 30 and 50,000 pounds, I'm probably getting all my bands inconsistently. You get 10 points and 20 points or whatever, and then you get something for the number of credit cards you've got, and you get something for how long you've lived in your house and how long you've been in your job. These are typical sorts of things. It might seem that completely explains the model, but because you can just add up the number of points and see what your score would be and work it out. But it disguises the fact that although that seems like a completely linear model, because you just add up, and in terms of its variables, it is a completely linear model. If you have correlations between those variables, which you typically do, then actually the model itself ends up having nonlinearities in it that are hard to explain. And so what that means is if you take the scores produced by the model and you break them down by the input variables, you end up with scores that are not the same as the points allocated to each thing. Because if you have 2 different things that are correlated, like the size of your house and your income, for example, then you'll get a lot of points for each of those. But when you look at the combination, it won't just be the sum of those 2 things. So you can use those kinds of techniques with synthetic data generated in that way as well. Does that sort of answer?
It does. We've explored some of that with some of the more statistical based models we do. And yeah, just wondering as we looked at different synthetic techniques, whether it's
and I mean, in terms of the techniques that are out there, one of the easier ones to explain is fully conditional synthesis, which is most often implemented through carts. So the first column is just a one-dimensional distribution. The second one is a single outcome. Well, in fact, all of the further columns are single outcome things, but the second column only uses values from the first column to predict it. The third column uses values from the first 2, and so forth. So those are relatively explainable synthetic data generators.
So I have a question that might be Eric or Victor. I'm not quite sure where this will fall. I wanted to know what makes the German simulation different from the UK. What is it that you put in to make it different?
Well, there are largely 2 main distinctions here. So first of all, we have maybe the simpler approach here is that we have free text elements, or we have things like to which merchants do people to go to for shopping, etc. And these would obviously differ from country to country. Like I probably wouldn't go to Waitrose in Spain if there's no Waitrose. But there are also perhaps more important things like the statistics we base the economy on that we simulate. And Victor already mentioned earlier that we at the moment largely use publicly available statistics from the German government page, where, for example, we determine the population demographics, how many male and how many female people are there, which in turn might affect how much money they spend and how often they go shopping, etc. And that would also be one aspect where Germany would differ.
Okay, so more a question of a cultural difference. So if we then moved over to simulating the Spanish economy, we would take in the cultural differences there of when people shop, rather than not where they shop, but when they shop, or
that could be very plausible. When
Spanish eating habits.
Yeah,
might be slightly
that's what you. I know that you were mentioning Spanish eating habits.
Yeah.
But I think more generally, actually, I'd say that the simulation is relatively simple at the moment. So there are differences. There are the distributional differences in the reference data and so forth that we talked about. Holidays, all sorts of things. Yeah. But as we start adding more behavioural elements as well. So one thing that would obviously be different even today is we have council tax in Britain, whereas the local government taxes are different. So different tax rates, all those kinds of things factor in. But also attitudinal things factor in. So if I go back to my road traffic simulation, I might get into trouble here, but we not only had cars and origins, destinations and drivers, but they had levels of awareness and aggression. And so when we modeled Germany, we gave rather different levels of aggression and awareness from when we modeled the UK, both of which were higher in Germany in the simulation, right? Based, I should say, not on some racist assumptions, but on measured data that we had from Germany and Britain. Average driving speeds were higher as well. So I think over time, more and more of that will come into the simulation. And so that our agents don't, they do have preferences, but they don't have very many preferences and things that distinguish them. Over time, that's a lot of the richness that we'll be adding in, and then we can incorporate more and more societal differences.
Any more questions in the room? Could you come up so we can't hear you? Sorry. The microphone's here. Sorry. Technology is against me for the microphone. It's just easier to bring everyone to the front.
Thank you. Hi, everyone. Thank you so much for the really good and useful presentations. I'm Marina from the University of Edinburgh, the business development side, not the academic side. So thank you for simplifying for sort of non-technical people. I'd like to think I understood most of this. My question is, so you've mentioned the example of working with FCA in sort of cybercrime prevention, which is really commendable and an excellent example of using synthetic data for good. Do you work or are you aware of any other parts of the government, for example, Treasury, using synthetic data or simulation models prior to perhaps making some major fiscal decisions? Sort of, are these things modeled to see whether the UK population or even wider can take some fiscal changes that might kind of affect everyone? Do you know if that is used?
Got any fiscal changes in mind?
I was going to say the synthetic government that you mentioned, there might be a reason about that.
I mean,
Yeah,
With a sort of robotic leader and that sort of thing.
Your words, not mine. They're on camera as well. So this question, do you work with other parts of the government, and are you aware if these models are used, and could they be used? A bit of a general question, but thank you.
So I think we are looking at other parts. So we work quite closely with other parts of government. We do supply data to them. At the moment, actually, most of the data that we're supplying is aggregate data from our data suppliers. So for example, it's public that we get a feed of weekly de-identified data from NatWest about their current account customers, which we do produce safe aggregate statistics from and feed into government. And that goes into the Treasury, it goes into BEIS, it goes into Scottish government actually as well. It goes into all sorts of places. And that has been used to understand what's going on with COVID. We do something similar with small businesses, from accounting firms, to understand what's going on. Specifically, we're in the process of looking at what's going on with the energy crisis and stuff like that. Now, none of that is synthetic at this point. This is all real data. I think there is interest in synthetic data from a number of these places outside the regulators, though I think the regulators have particularly strong interest. So we've been working with the FCA and the PSR, but there's a thing called the UK Regulators Network, which includes, Ofgem and Ofcom and Ofwat, and all these things. And there's a lot of interest in this approach in a lot of those areas. I think more generally, we see, when you talk about are there models, the Treasury and the Office of Budget Responsibility famously have a model which is, in terms I was using earlier, a macro model that has, an inflation rate and an interest rate and an employment rate and things like this, and rolls that out. And famously, according to everyone you ever hear in government, it's always wrong. But it's kind of better than no guide at all. So I think there is a sort of dream that, we've only been doing this for less than a year. Our hope is that if we continue developing as we intend to the simulation that we've got, and calibrate it more. So one of the things we haven't fully done yet is calibrated the outputs and the behaviors that are happening to aggregates that we take from various data sources that we have and various official sources. We're doing some of that, but we haven't done all of it yet. But as that model gains more credibility, you can imagine, and particularly as we add in full modeling of the businesses as well as of the people. I mentioned that we're doing this kind of half modeling of the people. I think you could imagine that potentially becoming something that might start to produce more interesting outputs at a micro level than the Treasury model. So at that point, that might be interesting. One of the hopes that we have is that the software that we're working with for the agent-based simulation will potentially be something that expert researchers can come in and replace particular components. If you've got a gambling expert, they can come in and kind of replace the gambling behaviors that we've got in the base model with, you know, various models that they have that might be a lot more detailed, that might allow them to explore the effects of different policies on gambling, those kinds of things. So it's early days, but I think we do see a role for it.
So you mentioned privacy versus utility, but what's your experience of confidentiality? So, like giving you all my data, and even if it's simulated, could give you an idea of my mortality rates in a hospital, or give you information about my operations that I'd be concerned about. What's the culture? Because it kind of assumes an openness to be analyzed, I guess.
Yes. So there is always this concern, and it exists in the health context. It exists in the financial context as well. You know, how comfortable are people with knowing or with information being disclosed about, you know, the wealth of people in big houses in Barton or whatever. I guess there are a lot of these things that are not, in fact, treated as private by most governments. So the ONS collects data, collects census data, people have to complete that, and that's regarded as public data. That's published, and you don't have much choice. There's obviously a difference when it's non-consented data. I mean, in some sense, the government census data isn't consented, but it's mandated. Whereas, obviously, if you take information from a private organisation where you haven't had that consent, then that becomes different. Now, under GDPR, there are obviously a number of different justifications for using data, one of which is consent, which is normally regarded as the best justification for use of data. But there are also legitimate interest things, and there are specific research opt-outs. So there are definitely legal bases that allow these things to happen, which is kind of dancing around the fundamental question of how do we feel about potentially revealing things that people might not want to know. And I think it's an active area of concern that we all have to think about. There are clearly there are trade-offs, right? And the trade-off is that there are big social and societal benefits available from policymakers and people generally having more accurate information about what's going on. And there are legitimate concerns that many of us have, certainly including myself, about not wanting, the state or everyone to know everyone's business. And I think, that's a question that has to be thought about all the time. We rely largely on the legal frameworks and the ethical frameworks to put those things in place. Certainly, SDF has a very strict system of DPIAs that get carried out before we do any work, both before we accept data and before we release data, and we're reviewing that all the time. But I think there's no one size fits all answer. If we don't make any data available, then we get real losses as a result of that. And it protects criminality, it protects bad behavior and so forth, as well as protecting legitimate privacy. We have to as a society decide. Clearly, different societies are very different about that, right? Scandinavia, many parts of Scandinavia, tax returns are completely open, whereas that's almost unthinkable in Britain.
Time for one more question. I think we're good to wrap up. Thank you very much for taking the time today. Thank you everyone for coming and online. Thank you so much. If there's anything that you want to ask, you can just pop that in the Q&A and I can get them to the panelists. Otherwise, you can email, and this session was recorded, so I will be emailing you out the link to it as we come. Thank you.